afternoon. Thank you for letting me explain a little bit about our company Picosun and the applications of atomic layer deposition. And in the end I will explain also about the systems we are making for atomic layer deposition. Okay, it's hard to see the slides here, but Picosun was established in 2003 and we have experience in atomic layer deposition since 70s. We sell systems made in Finland for global markets for both R&D and production, and at the moment we are over 10 million euro company, and we are growing at the pace of 100% per year. And because of the design that is unique to our reactors and our background, we think that we can successfully scale up ALD for new applications and also win in the global competition for ALD market. And the team consists of more than 35 persons, and out of this we have 11 or 12 PhDs now. And some of them are also Russian speaking, so I'm sorry, I'm not one of them. So worldwide we are based in Espoo, Finland, and we have the headquarters in the Micronova Center near Nokia headquarters, and our factories in Masala near Espoo. So these are pretty close to St. Petersburg. I just took a train, it took me 3.5 hours to get here. And then we have our offices in Detroit and in Singapore, and global support. We are working in Russia with the Trade House Scientific Equipment, TDNO, and we have systems in St. Petersburg and Moscow, for instance. And globally we have companies such as IBM and Bosch which are using our systems. So the principle of ALD is that we are working with the surface saturated, well-separated reactions between molecules and chemisort molecules on the surface. And after every molecule pulse, we purge away the excess molecules and byproducts and only leave the molecules that have reacted with the surface groups. And then we repeat by introducing a second pulse that will react with the first molecules on the surface, and then we purge away the excess precursor and reaction byproducts again. And by repeating this cycle we can grow films bottom up like piling Lego bricks, so that we can make a digitally controlled process and on all three-dimensional surfaces, also in nanoscale, like nanometer scale trenches and vias and micro cracks and nanowires and nanotubes inside nanopores, but also on macroscopic objects, because these gases, they see all the surfaces and react on all the surfaces. So the advantages of ALD are comprised of the surface controlled method, which is giving these special characteristics of ALD films in every forms of ALD. So instead of nucleation and crystallization step, we can have directly organized films with no pinholes, with less impurities than in CVD, and effectively you are purging away the side products twice per cycle. You can have lower process temperatures because we can use more aggressive precursors than with CVD. And instead of source control, we have surface control to lead into very conformal and very uniform films. ALD precursors can be grouped into inorganic, like chlorides or other halides, and metal organic and organometallic precursors, and these have certain advantages and disadvantages, and we have spent a lot of time finding out what are the suitable processes and precursors for each material by ALD. So this is a list of materials which we can make, and many of these have been made the first time in Finland, and for example last year we made as the first company gold with ALD on full-scale 8-inch silicon wafers. So here's some of the application areas for these ALD films. I won't go into detail of all of these, but I have some cases as examples later in the presentation. So mostly ALD is used in semiconductors, where Intel Corporation has started to use ALD in gate oxides since 2007, and also the DRAMs in the world are made with the ALD, and there are other applications like hard drives which take use of ALD. The ALD is also used in optics and MEMS devices as different wear resistant and anti-corrosive layers, edge barriers in nanostructures inside pores, around AFM tips, around particles, and around nanotubes and wires. And then there are new applications coming up for solar, fuel cells, supercondensators, and thin film batteries. And we have been able to make anti-stiction layers and nanoglue layers and biocompatible layers, also magnetic and ferromagnetic layers. And now there is this continuous ALD coming up for roll-to-roll applications on printed electronics. But mostly ALD is still used in the microelectronics. So I wanted to take up one application which we have lately had success in. It's using ALD as a diffusion barrier against corrosion, and we had a 3-year-old project with the EU and several large corporations in automotive, aerospace and gas industries, and we have been able to develop a coating called Coral, which is reaching 600 hours in salt mist spray test, and standard in automotive industry is 192 hours. So we are already in production with this application. This is something that we have also utilized this nanocluster in Finland to help in developing this. ALD started in Finland from the electroluminescent flat panel displays. They are still produced with this technology in Finland, Espoo, near our factory. And new displays, for example OLED displays, can enjoy the good properties of ALD films as well. ALD is coming up fast in solar cells, and with the Picosun tools we have been able to increase by passivation the free carrier lifetime from 3 microseconds to 10 milliseconds, and to improve the silicon solar cell relative efficiency by 5%, so absolute efficiency more than 1%. These are pictures from IMEC. Then with this Hungarian Science Academy, we have been able to develop a buffer layer for CIGS solar cells, which are thin film solar cells which normally use cadmium sulfide as buffer layer. And this is a problem because of environmental effects. So we have been able to make doped zinc oxide film, and also there are several other customers in the industry that are working with this right now. For fuel cells, we have PM fuel cells where ALD can be used as catalyst, and then solid oxide fuel cells where we have projects to make the ceramic solid oxide, and also ALD can be used for corrosion protection in this. So there are several projects and customers in this application area as well. Okay, then for the most well-known application, this shows ALD film is the one that is 2.28 nanometer thick. This it shows the Intel microprocessor, and this basic process development and tool development for this application was also done in Finland. After some time, this was taken into full-scale production in Intel Corporation, so it took more than 10 years actually. Then the reed heads, ALD is the only film that can reach 10 megavolt per centimeter around the corner, coding into the gaps and passivation of the reed head in the hard drives. So we were told by a hard drive manufacturer that ALD technology more or less saved the whole industry, because they were facing a brick wall which they couldn't break otherwise. In microelectromechanical systems known as MEMS, we have several different applications in ALD. There are, besides this wear and tear coatings and dry edge barriers, we can tune the oscillators, we can have anti-stick and gluing layers, and charge dissipative layers, conductive layers, insulators, and so on and so forth. About our systems, we are building both R-series and P-series systems. The R-series systems are very flexible modular systems for research, and the P-series takes use of the same flow design, but it's scaled up, and we have added automation so that this can be used for full-scale production. And with our systems, we have reached at best 0.13% uniformity is 1 sigma on 8-inch wafers, and then the defect levels have been 1 to 2 particles larger than 70 nanometer on a full 8-inch wafer. So these are fully capable production systems. We have also spent a lot of time developing a plasma-enhanced ALD, where one of the precursors, the non-metal precursor, is activated by inductively coupled plasma, and it becomes as radicals on the surface, and by this we can grow transition metals and many other materials with lower temperatures, or find alternative reaction routes which are not possible with thermal methods for ALD. So we have very fine plasma enhanced ALD systems also to offer now. Then these systems can be clustered with several tools, so you can separate oxides, metals, nitrides, polymers and sulfides into different modules and move automatically in vacuum or even in ultra-high vacuum from one module into another to keep the interfaces clean and to avoid metal cross-contamination. So these show some of our production tools, the platform and the P300 larger batch production tool, which can take 50 to 100 wafers in one run. And this shows a cluster tool with 4 ALD modules, which are also hooked up to glove boxes, because this is used for some poisonous processes. So as a summary, Picosun is a fast-growing company with a unique technology for ALD for industrial manufacturing. And we are welcoming all partners in industry and academia to join us for collaboration. And we are also committed to use this technology for building a better and cleaner world, and that's why we are part of the Clean Tech Finland organization. So thank you for your attention, and now it's time for some questions.